Okay. So for today, we will finalize this Mamba. Okay. So last lecture, we have learned about this Mamba, which is one of the state space models. Okay. So state space models compared to the RNN or transformer, they are uh, known to be robust to long-range dependencies. So they can model very long sequences. Okay. When the matrix A is properly set, this is their formula. So first, they are capturing the variation of the latent space using the input u and their latent space, multiplying some of the matrices on that. And also they are modeling the output using the similar formula. Okay, that's the SSM. And before deep learning, these SSMs are already used for control theory, but the difference is that in this nowadays we are using SSMs in the framework of gradient descent. So we are now wanting to train these ABCD matrices using the gradient descent algorithm. Previously, there was a closed form solution that can calculate this ABCD matrix given a few constraints. But now we are wanting to train this ABCD matrix using the gradient descent algorithm given training data. Okay, that's the difference. And when this A matrix is properly set, uh, I mean, these SSMs can properly model the long-range signals. Okay, that's the merit. And uh, we are calling that A matrix that can properly remember the previous history of this U of T, which is the input signals as the hippo matrix. Okay. Actually, there are some closed form solution for that. Okay. And also S4, they are also interpret this sequential, the recurrent process of the SSMs as the 1D convolutional filter operation, and they by I mean thereby they can achieve the efficient calculation of the overall SSM formula. Okay, they are interpreting this type of things as the one-dimensional convolutions where their kernel is set as these coefficients. Okay. But the thing is, the Mamba, which is the advanced version of this S4, is having additional selective mechanism. Okay, so not merely, uh, not merely propagate the sequential data. They are wanting to select the useful information and remove unnecessary informations. And uh, for doing that kind of selecting, the previous SSMs, their ABC matrices are constant. But here in the Mamba, they are wanting to additionally infer that ABC matrices from the input, okay, from the input, and also the latent space, their variables. Okay, that's the difference. So they can achieve this selective copying and also the inductive head things. Okay, but normally in previous SSMs, such as S4 architectures, they can only do this copying. And that's actually the motivation of this Mamba. And they are actually wanting to formulate this BC and the offsets as the estimated value from the input. Okay, so they are wanting to make it as the input dependent parameter, the matrices. For previous SSMs, they are keeping them as the time invariant matrices. Because of that, actually Mamba is losing very good characteristic uh, for the efficient calculation. So S4 that can interpret the overall SSM calculations as the one-dimensional convolution filtering, so they can apply very efficient uh, things. But I mean, in Mamba, due to this selection mechanism, their BC, their matrix is to propagate the signals across the time sequence is not anymore constant. So it is a little bit complicated to interpret those operations as the one-dimensional convolutions. So now they have to calculate all of the things recurrently, one by one. But even though this situation, they are wanting to do some selective scan by, I mean, retaining some of the operations in the HBM, which is slow, but doing some operations in the SRAM, which is faster than the HBM. So by doing this type of hardware-aware operations, the Mamba can retain the time efficiency as well. And this is the final Mamba architecture that is using SSM mechanism here and having some more modules like this. Okay. And this is the result for selective copying and inductive head tasks that we mentioned before. And Mamba architecture that is recording the state-of-the-art accuracy for selective copying and also in the inductive head. And especially here, they are experimenting the result, I mean, visualizing the result according to their time sequence length. And especially when time sequence, their length is very large, the Mamba, their performance is becoming stable, but most of others, their accuracies are getting close to zero when the sequence, their length is becoming longer. And now it might be time for us to extend the Mamba, which is the SSMs, to the visual domain. Okay, so Vision Mamba was the pioneering work for that things. Okay, so published in ICML 24. And they are wanting to, the slide has been changed a little bit from the previous one. I already uploaded that in the Blackboard, okay? So Vision Mamba, that is actually proposed to capture position sensitivity of the visual data and also the capture the global context, which is very important for visual tasks, okay? So we have to capture both, okay? Global context of the image data, and also at the same time, we have to capture the local spatial information contained in the images, okay? So here, that is very similar to Vision Transformer. They are using only encoder block and having the class tokens and also using the image patches as the tokens, input tokens to the encoder. Okay, so by doing that, I mean, Vision Transformer, VIT, that is also inputting the same signals, okay, the image patches and also the class token to output the improved version of the class token, and eventually that map this class token toward the class probability. Okay, that's the Vision Transformer. And anyways, they are also apply MLP and predict the final output after this encoder output. Okay, overall architecture are very similar to Vision Transformer, but difference lies in the encoder, their architectures itself. So these Vision encoders are now composed of the SSD, not as the self-attention mechanism of the transformer. So this is the embedded patches, okay? So denoting this type of divided patches, image patches, okay? And uh, the overall architecture of this is quite similar to previous architectures that we've seen here. So basically, from the input, they are having this type of residual paths, and some of the other paths having the convolution and SSMs. Okay, so in that sense, Vision Mamba, they are having the similar architecture with the original Mamba, but difference lies in this part. Okay, this part. So to properly capture both position sensitivity, which denote the local spatial information and also the global context. They are differently to the original SSM that has only one, how to say, one pass SSM. In the image domain, which is the Vision Mamba, they are having two passes, okay, that traverse the vision signals. Okay, what each one means is in the forward SSMs, they are traversing each patches in this way. So uh, this one first and next, this one and see this one next, see this one next, okay? So even though they are coming from the 2D images, okay, but they are seeing these image patches somehow in this manner, okay? So that's called as forward SSM. Okay, so I mean, originally the Mamba is working for the one-dimensional sequential data. So somehow they are losing the 2D information contained in the original images when doing only the forward pass. So in that way, in that sense, the Vision Mamba is proposing another streamed, uh, I mean, scanning method that scans the image patches in the backward orders. Okay, that is actually this new stream. Okay, so they are insisting that the author of the Vision Mamba, they are insisting that adding this additional path to see the image patches in different order can increase the ability to model the position sensitivity of visual data and global context for visual understanding. Okay, so actually, Vision Mamba, I mean, the motivation, the innovations has been made here. This part having both forward scanning and backward scanning to properly capture the image signals, which is different to the 1D signal. Okay, and by doing that, this method, Vision Mamba, they are experimenting their architectures in multiple visual recognition tasks. For example, image classification, semantic segmentation, detection, and instance segmentation, and they compare their architecture, Vision Mamba, their architecture, which is denoted as pink as the accuracy, with the date architecture, which is the enhanced version of VIT. Okay, so and they are observing that their Mamba architectures could become robust, more robust than the Vision Transformer, their variant. Okay, and this is the speed comparison. Still, I mean, compared to the date, which is the variant of the VIT, the Vision Mamba that is recording the faster speed and also recording the less memory consumption. Okay, but recording the better accuracy. Okay, that's the Vision Mamba. And the name of this method is also very similar. Their title is very similar to Vision Mamba, but that is also doing the similar things to apply Mamba architecture to the visual recognition tasks. And that is called as, I mean, that is also published in URIPS 24. Okay. And their method is also similarly motivated to the Vision Mamba, but having some more modules compared to that. Okay, so this is the image patches, similar to the Vision Transformer or the Vision Mamba. They are dividing the overall images into several patches. Okay, and compared to forward and backward traversing, in Vision Mamba, this V Mamba is proposing four types of traversing method, which is this one, seeing patches in this order. So 1, 2, 3, 2, 8, 9. Okay, that's traversing the patches in this manner. And also, we can also traverse the patches in this order: 1, 4, 7, 2, 5, 8, 3, 6, 9. That's the the thing denoted here, right? And also, we can do backward things for this type of things. Okay, so we see 9 first, 8 next, 7 next, 6 next, 5 next, 4. This is the order of the traversing when doing things in this order. So they are traversing the image patches in this way. And also we can traverse the patches in this way. Okay. So in this VMamba, they are proposing four scanning method, okay, in this order. And they are separately for each scanning method, they are having separate SSD operations, okay? And then they are getting the final feature and then concatenate all the information to uh, get the final feature from the SSD blocks, okay? So that's the main module proposed in the VMamba. Okay, are you guys following? This is easy, right? So compared to the self-attention mechanism of the VIT, which see dense, this is the query block, and in the attention mechanism, they are densely see all the patches nearby, okay, to get the final the Q and K their dot production. For getting that, we have to see all the nearby pixels, but in the SS2D, which is the new scanning method proposed in VMamba, they are only see patches 4 times in this traversing order. Okay, that's the thing proposed by VMamba. And also, this is the overall architectures of the VMamba. Okay, so and also this is the VSS block that is having the SS2D block here. Okay, so compared to the original Mamba block, they also have using some heuristic experiment, they are observing that composing the block Mamba block as this is more effective than having this type of Mamba blocks in the visual domain. So they are little bit changing their architectures like this. So this is the new VSS block, okay, visual state space block, okay. And using that VSS block, from the input images, they are partitioning the input images into multiple patches and apply this VSS block multiple times, okay, to get the final output. That is the VMamba architecture, okay. And also later, I will explain that later, okay. So VMamba, that is somehow they are the author of the VMamba, they are insisting that their scanning method for uh, they are dividing the scanning method into these four scanning, right? And to say this is visualizing the scanned output from this traversed order, and this is also visualizing some the output for this order and this order, this order. And when merged together, we can interpret those combination of full traversed output. We can interpret it similarly to the original attentions. So this is the original transformers attention, their activation map from this image. And they are saying some of the important objects are their locations are highlighted in the attention, their maps. Okay, and VMamba as well by integrating these four types of traversing their activation maps. This is the merged activation map of the V-Mamba activations, and we can interpret uh, these important object regions are also highlighted. Yeah, but I mean, of course, they are becoming more sparse, but while capturing the important object, their locations. Okay. So they are comparing their four types of concatenation of four traversing things with the attention mechanism of the transformer. And also this is showing the receptive field of the several CNN and transformer and Mamba architecture. And this is the receptive field of the CNN, their method. Receptive field, you can interpret this as seeing the nearby pixels context. Okay, receptive fields, roughly we can interpret if you have a larger receptive field, you can think this as uh, exploiting more context from the nearby pixels. CNNs usually, I mean, we are that CNN is local operations, so we are, I mean, having some context, receiving some context from the nearby pixels, but that nearby pixels are bounded by some filter corners, their sizes. Okay, and transformer, their receptive fields are becoming more larger than CNNs. Okay, and also V-Mamba, you can interpret, thanks to the long range, the ability to model the long range dependencies, especially in the Mamba, we can have larger receptive field. Okay, so you can see the V-Mamba's receptive field is also very large. Okay. Okay, so that is the V-Mamba. And the next thing we have to see is the Mamba YOLO architecture. This is, uh, the object detection algorithm. YOLO, you may remember that YOLO is one of the successful object detection pipeline, which is real time. And Mamba YOLO is also the real time object detection pipeline that is using the Mamba, their core operation. And this is the overall architecture of Mamba YOLO. And this part is showing the simple stem block of this YOLO Mamba. And this is showing the vision clue merge operations in this part. Okay. And also the core part uh, that have the SSM operation in Vision Mamba YOLO is ODSS block. And that part is actually explained here, okay? So we will see, okay? So object detection algorithm, similar to previous extension when extending the image classification network towards the YOLO, we are trying to somehow increase the resolutions of the images. And similar strategy have been used in this simple stem algorithm, their networks. So previously in Vision Mamba, we can see the original images are in this resolution, but when partitioning the patches, we are simply reducing their resolutions by the factor of 4. But in Vision YOLO, this simple stem is somehow relieving their information loss. When abruptly divide the overall image resolutions by 4, this Mamba YOLO is saying that that is losing too much information, which might be essential for the object detection task. So in the simple stem, they are they are applying convolutions 2 times to, gradually reduce the image size by the factor of 4. Okay, that is simple difference to the original V Mamba here. And Vision Clue Merge, that is also some modules which is proposed in the Mamba YOLO to relieve the enveloped resolutional reduction. So previously in how to say uh, Mamba, uh, this is let's say this is the original 2D feature map, and by flattening those patches into one-dimensional signal, we apply the subsequent modules. Okay, that is how the Vision Transformer or how Vision Mamba they are using the image patches. But if we select only one patches in these sub-regions, normally we select only one patches similar to the pooling operation, but that is aimlessly losing too much information. So Vision Clue merging, they are wanting to select one patch from each sub-regions, but still want to not losing all other information or all other unselected information. So this part, this later part, these three patches which is removed are concatenated for the selected patches. That is Vision Clue merging. So additional Vision Clues are merged to the selected patches. That is the simple algorithm to increase the how to say the vision, prevent too much information loss. They are proposing this type of vision clue merging schemes to, and then apply the subsequent operations that is happening in this part. Okay, so this simple stem vision clue merge, those algorithms are proposed to not to lose too much information when doing the reduction in image resolutions. And these ODSS blocks are subsequently and continuously applied to get the first picture map. And then these ODSS blocks are later also applied to get the final feature map. And after that, for these three different hierarchies of the feature maps, we are applying the object detection prediction layer to obtain the final bounding box estimation and also the class estimation. That is the Mamba YOLO architecture. And in the ODSS block, this is actually the ODSS block that is introduced in Mamba YOLO. And what they do is they are involving this SS2D operation, which is proposed in VMamba, and having additional RG blocks, okay, to efficiently deal with the 2D signals. Okay, so this part is similar to the VMamba, but they are wanting to deal with the 2D signals more properly for the object detection tasks. So additionally add these RG blocks. Okay, so the intermediate feature maps are traversed in four different orders. Okay, and apply this scan merge operation using the SSM operations, and then further applied with these RG blocks to enhance the 2D encoding. Okay, and RG blocks, how they are organized is this is the original Mamba blocks. Okay, this is the original Mamba blocks, but they are wanting to add few more convolutional operations like this green box, and also add residual convolutions and gated operations, and gradually changing their RG blocks to gradually improve their accuracies. So this type of using via this type of heuristic experiments, they are confirmed that these RG blocks are accumulating more useful 2D information for processing the 2D object to deal with the object detection task. Okay, so these RG blocks are designed, okay, for the Mamba YOLO. Okay, so but I mean there are a few heuristic modules to retaining the local spatial information more efficiently compared to the original V Mamba in Mamba YOLO. Okay, so not to lose the spatial information abruptly, they are adding this type of algorithms, and then they are actually wanting to use three different scales of the feature map, similar to the deformable DTR or others. They are wanting to use multi-scale feature. Actually, they are wanting to use three-scaled feature and process it independently to get the final improved three different scale feature and then map it to the final predictions of the object detection. Okay, and here in ODSS block, they are composed of SS2D, which is the efficient version of the attention using the SSM mechanism. And they are adding few more architectural choices using the RG blocks. And Mamba YOLO, they are recording the good accuracy at the same time the real-time performance. Okay, that is the Mamba YOLO. Okay. This is some of the result coming from the Mamba YOLO, and this is the DTR variant, okay, and this is the YOLO variant, okay. And especially they are comparing their Mamba YOLO with respect to the Dino, which is the DTR algorithm. When their resolutions are not very high, this Mamba is providing very good uh, performance compared to the Dino, but when the image size, their resolutions are becoming larger, they are observing that Dino is still producing very good accuracy, but comparing Mamba YOLO in terms of the speed, uh, I mean, the Dino, their speed is exponentially growing according to the resolution, but Mamba is, increasing linearly according to the resolution. That is a good characteristic observed in the Mamba YOLO. Okay, but still, there are many things to be improved in the Mamba to properly applied in the 2D domains. So this is showing some limitations of the Mamba operations. So because Mamba is originally proposed for the sequential data where orders are important, but image pixels, similar to the transformer, their cases, image pixels do not have any spatial, the sequential dependency. Okay, so I mean, the V-Mamba, they are proposing very good method, which is the SS2D to improve this in some aspect, but still not very efficient in some cases. So, and also bidirectional SSMs, which has forward and backward, and SS2D, which has four different traversing order. They are wanting to capture more comprehensive context inherent in the 2D space, but still behind the, how to say, the state-of-the-art transformer-based architectures. Okay, so and also they are basically doing the things in the sequential manner, so their latencies are very high in the visual recognition domains. So, I mean, increased complexity, they can lead to challenges in training and risk of overfitting and I mean, not always better accuracy. Their accuracy is not state of the art compared to the transformers yet. Okay, that's actually the limitations of the Mamba in visual domains. So later, maybe more research have to be done for this, maybe. And Mamba Vision is actually one of the hybrid models that combines the attention mechanism of the transformer with the Mamba operations. And this is the architecture of them. So this is the image, and this is the patch division. And first part, they are applying the convolutional blocks, okay? And then they apply this block, which is the combination of Mamba vision with the self-attention of the transformer, okay? So actually, they are wanting to calculate to capture the global context using the transformer blocks, but still, I mean, Mamba Vision can also provide good information, good long-range spatial dependency information. So they are wanting to somehow mix these two operations, okay? And also slightly change their Mamba Vision blocks, okay? And getting the higher accuracy and given the speed limit. Okay, so this is the V Mamba, their curves, but Mamba Vision, actually the hybrid model that mix the transformer attention and the Mamba operation, they are recording better accuracy compared to the V Mamba. So, I mean, this type of further research have to be taken, I mean, to properly use the Mamba of their operations in the vision domain. Okay. So this is all for today's lecture. And maybe 2 weeks later, we will also review about some of the recent vision language models. Okay. And maybe next week, we will have the mid presentation session for the final project. Okay. So for today, let's finish here. Thank you.